Hello everyone, I'm Yash Bhargava, and today I'm going to walk you through how to do a molecular dynamics simulation using GROMACS, starting purely with the sequence information of a heterodimer. So first you need to know what you're going to simulate. So let's say you're just reading through a paper like this one, and you see some interaction that you're interested in simulating. So in this case, we're going to be simulating CXCl4 and CXCl12. The first step is to get those sequences. So let's search up CXCl4 and also CXCl12. UniProt is a great resource to get this information. Let's choose Homo sapiens. Let's use this entry. Then Homo sapiens CXCl4, this one. We want to get the sequence. So for both of these, we can grab sequence information, and you can see that right here. So let's copy this down and note it for each of these. And now the next step, once we have the sequence information, is to get a starting structure that we can do our simulation on. And a great place to do that is AlphaFold. They have a very convenient web server, and we're going to use that for today. We can use it like so. And let's just call this CXCl4, CXCl12. So now this will run. Usually it'll take 5 minutes, but I think depending on the load and the size of what you're predicting, can vary. So let's wait for that to finish. Okay, and the simulation is complete, so let's take a look at that. And here you can see the predicted interface. Interesting. So I do not like this large tail. So one thing you can do is you can trim that off, but I'd actually like to see what it does in the simulation. So we can just have a pretty large padding to allow this tail to move around more freely. Yeah, usually you'd want to trim it off, but let's see what the full length does. So you can download the structure and port it over to your machine where you're actually going to do the simulation. You want to get the model0.sif. Okay, and I've got the file over on the workstation where I'm going to run the simulation. And right now, AlphaFold will output your file as a CIF, as you can see here, but it's usually easier to work with PDB files for the purpose of simulations. So one tool that we can use is obabel, which I have in this Conda environment. So let's do obabel, and then you type in the file name, and then -o for output. And let's just output this as complex.pdb. And there it is. Let's also actually make a folder for this simulation, CXCl4, CXCl12. All right. So now we have everything in there. And now we can actually get started. So let's use, I'm going to be copying over some commands and explaining them. Okay, so now we have our complex.pdb file and our CIF. We're not going to use the CIF anymore. We're going to move forward with the PDB. So let's use GROMACS. We're going to convert this PDB into files that GROMACS can understand. So let's put in our file, and we're going to output complex.gro, topology file, keep going. Okay, so now you're going to get a list of force fields. Basically what that command is doing is taking your input PDB and turning it into files that GROMACS can understand. Let's use this force field here, number 6, amber 99 ILDN. So we can choose the default recommended model for waters. And now we have our topology file. So you can see we've got a bunch of files here, one for each of the chains. There are 2 chains because it's a heterodimer. And now what we're going to do, you might actually, depending on the force field, be prompted to choose the termini if you use the -ter. And in that case, you'll usually want to choose NH3 plus and COO minus. Alright, next let's build the simulation box. And we're going to basically be taking our GROMACS files and putting 10 angstrom padding around it and doing a dodecahedron. Because we had such a large disordered region, I'm actually tempted to do 20 angstrom padding. Let's just try that and see what happens. Okay, so we've made our box, and the next step is to actually add water to this box. So we can solvate this, and there we go. Now, one thing you want to look at is the density after you add all the water molecules. It should be around 1. This will be slightly different because it's not pure water. You also have your protein, but this looks good, close to 1 kilogram per liter. And the next step is to do an ionization. For the purpose of this simulation, we're going to do it with 15 molar sodium chloride. So you can create an ions._em.mdp file, and you can just choose the settings here. Let's do a quick one because we're going to basically be doing the solvation, so it doesn't need to be too rigorous. I will include all these commands in the description. Okay. And you will see that we are added our sodium and our chloride ions. Nice. The next step is to do the actual energy minimization after solvation. So for that, we can first create a .mdp file. And now let's generate, so this gromp command will generate the files to prepare for your simulation. So now it says that this run will generate 32 megabytes of data, and the reason that it's large, yours will probably be less if you do less padding. That's why it's pretty large. And now we can run the energy minimization. Okay. So you can see that a lot of things are rotating quite a bit. It gives you a warning if something rotates more than 30 degrees. That's just a sign of bad input structure geometry, which is something that AlphaFold it does sometimes provide clashes in your structure. But you can see the warnings have stopped after step 44, so we're already looking pretty good. And the next step is to equilibrate the temperature in the NVT ensemble for 100 picoseconds. And that will basically be keeping the protein restrained, and see how it behaves here. So this might take some time. I'll be back once it's done. Okay, so it looks like our energy minimization has stopped, but we weren't able to request like the minimal convergence, but it's okay for now. Given these parameters, it is minimized. Definitely you'll want to pay more attention when you're doing your own simulations to this kind of stuff. So now we can do NVT. We'll use these settings to do 100 picosecond. Prepare it. And now let's actually run this, 54 megabytes. And yeah, we'll be back once this one's done. Alright, that's done. So now we can do the next step, which is where we do NPT. Once again at 310 Kelvin, 1 bar of pressure. So we make the file npt.mpt, and let's run this in a screen session. If you have to run a command and leave, you can just do it in screen. Okay. And now we can leave by pressing Ctrl A and D. The reason the simulation is so slow is because not running on the best hardware.
Alright, and yeah, you can see that the 1 nanosecond simulation is complete. And now the system should be ready to do an unrestrained simulation, or a simulation with less restraints. So we can do a 100 nanosecond simulation. Definitely this would be faster if I didn't do the 20 angstrom padding. You should definitely check with your system. You can do like 5 to 10 if it's not having too many disordered regions that you think could self-interact. So let's go ahead with that. And let's prepare this command. Okay, now it's ready. 20 gigabytes of data, it's fine. And now we can start it. And yeah, make sure you do this in a screen session so that way you're able to leave by pressing Control A and then D, and it'll keep running and you can like resume from that. But yeah, that's an overview of the commands required to do this kind of simulations with GROMACS. The next step will be for you to process the simulation files and actually visualize the simulation. We'll get into that, and I'm also planning on making videos of actually going into the logic behind molecular dynamics. Thank you.